In our last video, we discussed the idea of countably infinite sets and how to show that a set is countable. In this video, we are going to show that not all sets are countable, that there are uncountable sets. And we're going to do this by showing an example of a set that is not countable. Okay, so we're going to use something called Cantor's diagonalization method, or technique or argument. Okay, and what we are going to prove, we're going to prove that the size of n is not equal to the size of r. Okay, so if we can do that, then this is going to imply that r is not countable. Okay, how are we going to do this? We are going to do a proof by contradiction. Okay, so to begin this proof, let's go to a new page. We are going to suppose that the size of n is in fact equal to the size of r. Okay, so what does this mean? This means that there exists a one-to-one onto function f that maps n to r. Okay, so for an illustration, and we're going to keep this running throughout, consider this table. Okay, so if the size of n is equal to r, which is what we are assuming, then we have this function f that's one-to-one and onto that's going to map n to r. Okay, this means for every element in n, I have some number, some element of r, and I don't know what they are, I just know that they exist. Okay? So on the left-hand side, I've got my elements of n, and the right-hand side here, I've got my elements of r. And these are real numbers, so they're infinite. Okay, so I know this exists. All right, so what's our objective? We want to find a contradiction. We want to show that our assumption is not correct. So we need to be able to find an element, x and r. Okay, so our objective, we want to find an element x and r. We're going to say such that there is no element n. There is no n. Such that f of n is equal to x. Okay? So what we're saying here is that there is some element in the real numbers that isn't mapped to by f. That's what that means. There is no number in the set of natural numbers. There's no n. This more specific, no n in n, such that this map that n to that x. Okay, and if we can find this, then we've shown that f is not onto. There is some element in our range that isn't mapped to by the function from the domain. Okay, and so this is going to show that our function f is not actually onto, which must be the case. It must be onto if these two sets are the same size. Okay, so if we can do that, then we have our contradiction. Okay, so how do we find this x? We're actually going to construct it explicitly. Okay, so let's start on a new screen. So we're going to actually construct x. One of our restrictions for this x, just to make it easier, is actually going to be that x is going to be a number between 0 and 1. Okay? And x is a real number. So what do we need to do? We need to ensure that for any n in the natural numbers you give me, x is not f of n. That's our objective. So let's start constructing x. So first thing that we want to do is we want to ensure that x is not equal to f of 1. Okay? So refer back to our table. Okay? All right. So I know that there is some number here for f of 1. All right, and I want to ensure that x is not that number. Well, it must be some number. Let's suppose that it is this number. Okay, once I know that this function exists, I know that this number is some number. Let's just suppose it's that one. This will work even if it's any other number. Okay, and you'll see in a minute. So how we're going to construct x is we're going to make, so here is going to be x. Here's my construction of x. It's between 0 and 1. So I'm going to make sure that the first fractional digit of x differs from the first fractional digit of f of 1. Okay, so what is that? Here it's 1. Okay, so we'll make x, the first fractional digit of x, we'll make it 2. Okay, they're different. Because they're different, I don't even have to look at the rest of x. I know that x is not equal to f of 1 because it differs in that digit. And that's all I need to know. If it differs in one digit, it's not the same. Okay, so the next thing we need to do is we need to ensure that x is not f of 2. Okay? And so what we're going to do there is we're going to make sure that x differs in the second fractional digit from f of 2. Now, right now I don't know what f of 2 is, but if this function really did exist, I would know what it was. So let's suppose that it's this. Okay, so I'm going to find the second fractional digit, which is a 5. So I'm going to make x anything, the second fractional digit of x, anything but 5. So let's just make it 6. Okay, so now I know, just by looking at those two digits, that x cannot possibly be f of 2. So now we want to ensure x is not f of 3. Okay, again, I don't really know what f of 3 is, but let's suppose that it's this. Okay, so I look at the third fractional digit of f of 3. It's a 3, so x needs to be anything else. So let's make it 7. I'm sorry, the third fractional digit of x needs to be anything else. So let's make the third fractional digit of x 7. All right, so I'm going to keep going. Okay, so maybe f of 4 is this number. Who knows? Okay, so I'll find the fourth fractional digit. Find the fourth fractional digit of x. It needs to be anything but 6. So let's make it 3. Okay, and let's do one more. Let's say that 5 is 317.024689. Okay, it keeps going. Find the fifth fractional digit. It's an 8. So the fifth fractional digit of x needs to be anything else. Let's go ahead and make it a 5. Okay, and this keeps going, right? These keep going. So we also know here x is not f of 5. Let's make that a little bit more. There we go. So, excuse me. I don't want to keep repeating this, right? We could do this forever and this video would never end. So I need to know that no matter what I do, x is going to differ. And actually, the way we're constructing x, if we repeat this pattern, we will actually have that assurance. So what we can say is that for any n in the natural numbers, any element of the natural numbers, we're going to know that x is not f of n, because x is going to differ from f of n in the nth fractional digit. Okay, so let's write that so that we can see that that's true. We're going to write for any n in the natural numbers, x is not equal to f of n. Why? Because x differs from f of n in the nth fractional digit. Okay, so that's pretty awesome. What do we have here? We have an x in the real numbers that is not mapped to by any natural number. And if we remember, that's our objective. We needed to find this x, and we have. So by achieving this objective, what do we have? We have, let's make that cleaner. This pen is a little crazy sometimes. Okay. We have our contradiction. So what did we assume? We assumed that the size of n was equal to the size of r, and we know now that is not true. Okay, so this also tells us that r is not countable. Okay, and that's what we set out to prove. So that's very exciting, right? So I just want to very quickly address one concern that you might have. So if we look back, we remember that our assumption that n equals r implied that there exists a one-to-one onto function, okay, that maps n to r. This is not, so you might say, well, what if there is a one-to-one onto function f that maps r to n? Haha, right? What about the other way? We didn't deal with that function. We dealt with a function that mapped n to r, but what about a one-to-one onto function that mapped r to n? If we could find that, then we would still have that the size of r is equal to the size of n, right? So I just want to remind you that if we have a function f that maps, say, a to b, and f is one-to-one and on 2, what does this mean? So we have a to b. It meant a couple things, right? One-to-one means that for every, we'll make these infinite. Okay, it meant that for every element in B, we have at most one element in A mapping here. Okay, it means we never have this case, right? That does not happen because it's one-to-one. Okay, and it also meant by being on 2, it meant that for every B, there is an A such that f of A is B, right? So now the question is, if this exists, if this f exists that maps A to B that's one-to-one and on 2, is there an f prime such that f prime maps B to A? And yes, in fact. If you can take, so here we can take the inverse, right? I can take an element from B and I can map it to A. So I could take this, this function and basically invert it and be able to go from B to A. Okay, so just in case you think that this assumption is problematic because we're only taking a function that maps n to r, I just want to remind you we could have gone the other way. Okay, so either way, the size of n is not equal to the size of r. Okay, pretty cool.